Hello everyone, welcome to lecture 2 of Applied Geophysics. In this lecture we're going to cover chapter 6 of the textbook, which is about elastic waves in the continuum. Chapter 6 consists of 13 sections. In this lecture 2 we'll cover from 6.1 to 6.6, and the rest of the sections will be covered in the lecture 3. So let's start. So why we are interested in mechanical wave? Because mechanical wave causes the minimal perturbations, so without causing any permanent effect or altering ongoing process. This observation is the foundation for dependable and versatile testing method based on the propagation of elastic waves. So we use elastic wave because it doesn't affect the ongoing process, and we can use this one to monitor the ongoing process inside the like soil medium or particulate medium. So this chapters on the propagation of a mechanical perturbation in elastic material. So we'll see the elastic waves in the elastic materials. So first, terminology. The wave, the amplitude varies with time, and in this amplitude versus time we can define the period. Period is an interval of time between the reoccurrence of phases in a vibration, and frequency is the measurement of the number of times that a repeated event occurs per unit of times, and unit is 1/second or hertz. Angular frequency is a scalar measure of rotation rate. So W, the omega, is defined as, is the blue one, 2 pi f. So then this could be 2 pi over capital T. And also wave travels through the media over a distance. So you can plot the wave amplitude over distance, then now is its amplitude versus the distance in a spatial scale, and this one is temporal scale because the time changes, and here distance changes. So then the wavelength is the distance between repeating units of the wave pattern. So from peak to peak, that's gonna be in meter, and the wave number is a wave property inversely related to wavelength. So having units of the inverse length, like cycles per meter, and wave number is the spatial angular frequency of a wave. So kappa is the wave number, and kappa is defined as 2 pi over lambda. So if you look at in temporal scale and spatial scale, then temporal period is t and spatial period is lambda. So from peak to peak, from another peak to peak here, and angular frequency omega is 2 pi over t, and spatial frequency is kappa and 2 pi over lambda. And one note is that the wave velocity is estimated, or it can be computed by multiplying the lambda and f, so the wavelength and the frequency. So here we're gonna talk about the wave propagation in elastic materials. And here elastic material, we assume it's infinite medium, so there's no boundary, and linear elastic. So when you apply the force, deformation increases linearly, and when you unload it, it goes back without any hysteresis. And isotropic means that if you apply the force at this direction or this direction, the deformation is the same. So k, x is ky. The elastic moduli doesn't have the directionality. Homogeneous means there's no like speckle or the heterogeneity inside. It's a uniform material. If the wavelength is significantly larger than the characteristic dimension of the medium, then wave traverses the material as a continuum. So for example, the wavelength is like 1 meter, and if the particle is like 1 centimeter, so then the wavelength is much larger than the particle. So then wave will not feel the material is discontinuous. Right? You will feel as a continuum material. So we are assuming that the wavelength is much larger than the characteristic length of the material. So as a governing equation in elastic to describe the elastic wave propagation in continuum material, there are several governing equations to define. First is the equilibrium equation and compatibility equations, and the last one will be continuum equation, the constitutive equations. So we'll go one by one. Equilibrium equations is based on the force equilibrium and the momentum equilibrium, and the final equation is like this. And this one is in the one direction, along the x direction. In compatibility equations, it defines the strains, and normal strain, and shear strain, and volumetric strain. And here, one notice the engineering shear strain is not the same with the pure strain. Actually, you have to double the pure shear strain to get the engineering shear strain. Increment is delta, that we use this symbol, and the strain due to stress increment can be written like this. And as we just saw in the previous slide, gamma xy, gamma yz, gamma zx are called engineering shear strain. These are their magnitudes are the twice those of their counterparts, epsilon 1, 2, epsilon 2, 3, epsilon 3, 1 in the tensor notation. So constitutive equations relate the stress and the strain, or force and the deformation. So easiest constitutive equation is Hooke's law. So that relates the delta with the k, right? So when you have a spring, when there's a weight, and you have a deformation by delta, right? And this delta, the displacement, and the force is related by this elastic constant called spring constant k. And we can expand this kind of a concept for stress and strain relation. So Hooke's law relates the stress and strain through Young's modulus and Poisson's ratio. The result is this: epsilon z is related to sigma z and sigma x and sigma y. And shear strain xy is related to shear stress tau xy with the shear modulus g. And you can express that Hooke's law, the elastic constitutive equations, elasticity, using tensor notation like this. And if you expand it and simplify it for the x direction, and you end up with this equation: sigma x is lambda epsilon volumetric strain plus 2g times epsilon x. And here x lambda is defined as m minus 2g. Here m is the constraint modulus. And g is the shear modulus. And when you expand it, then you get this equation. So constraint modulus times volumetric strain minus 2g times epsilon y plus epsilon z is the stress in the x direction. And tau xy is simply correlated to the shear strain with the shear modulus g. Actually, the shear elastic modulus can be defined depending on the boundary condition when you correlate, when you establish a relationship between the stress and strain. So when the lateral deformation is allowed, like this. So here epsilon x and epsilon y is not 0. Then you can use the Young's modulus to correlate the axial stress and axial strain, sigma z and sigma epsilon z in this case. And on the other hand, if the lateral deformation epsilon x, epsilon y is confined, so if it's 0, so it doesn't allow any lateral deformation, then constraint modulus can correlate the sigma z and epsilon z. And here they used D. Sometimes people use M or D. So this is the case that we apply the oedometric loading. Simple shear, when you apply the shear stress like this, tau x or zx, then the shear modulus can correlate. And when there's an isotropic compression, like the balloon in the water, right? So here, this is the balloon, and you have an air pressure, then the deformation or the volumetric strain can be correlated to the bulk modulus B. So E and B and constraint modulus and shear modulus are correlated, or they are kind of interrelated through the Poisson's ratio. So then if you know two of them, so only two of these parameters are needed to characterize a linear elastic isotropic medium. For example, if you know the Young's modulus and Poisson's ratio, then you can compute the bulk modulus and constraint modulus and shear modulus. Right? So if you know maybe for example B and G, then you can compute the Young's modulus and Poisson's ratio and constraint modulus. So only two of these parameters are required to define and fully describe the elastic medium. So then we can derive the wave equation based on those equilibrium equation and constitutive equation and compatibility equations. If it's static, then force will be all equilibrated. But if the object is moving with acceleration, then it's called a dynamic condition. And then we have to assume the moving object with the acceleration a. So here the round ux over round t square is a. Huh? So this term is the acceleration, and this is the mass of the object. Okay. So then what about the constitutive equation? Constitutive equation that we derived before is this one right here. And here, let me write it down. Sigma x is m epsilon rho 2g epsilon y plus epsilon z. Here we can put this equation, these equations into here, and then we end up with this constitutive equation, right? So force, the equilibrium equations and the constitutive equation, we are just expanding it, and then we can derive and also expand it to simplify the equations. So this is the like very primitive form, and epsilon. Here, if you compute this one, you get this, and this, and here the g, you can take out the shear modulus out of the parenthesis, and if you expand it, because the epsilon y is what? Is round uy over round y, right? From the compatibility definition about the shear strain, then you can expand, and later you end up with this equation, right? And here, if you write it again to get the more simplified one, this will be the final wave equation in general. This wave equation is for infinite medium and body waves and linear elastic material and isotropic. So please derive these constitutive equations from the very beginning of this constitutive equation using the force equilibrium and the compatibility equations. And you can see that the wave velocity or the wave propagation and acceleration here is based on the m and g. So there are two modes. So that's governed by the shear modulus, and another one is governed by the m constraint modulus. Okay, the first mode is the compression waves. So characteristic dilation without rotation, particle motion is in x direction, which is the same with the propagation direction, and ux does not vary across the wave front in the yz plane. So then from the wave equation, we can remove these and these terms, and the remaining equation can be simplified to this equation. And you can see that this mode is only, this is the u, related to x direction movement, and also it's affected by the constraint modulus m. The motion of the point is parallel to the direction of propagation. So, and P waves travel through both solids and fluids and are filtered in the vacuum. So I'm gonna show this animation in the lecture later in the class. Actually, when you look at this particle, it moves to this direction. So back and forth, and wave propagate this direction. So particle motion consists of alternating compression and dilation, and particle motion is parallel to the direction of the propagation. So it's also called as a longitudinal wave. Material returns to its original shape after it passes. The second mode is called shear wave, and traveling in the x direction, but the particle motion is in the y direction. And ux and uz is 0, and ui does not vary across the wave front in the yz plane. So using this, we can eliminate the ux, ui, and uz term. Then you get this only. End up with this equation. And this describes the shear wave propagation. And it's also called the secondary wave, S mode. They are filtered in fluid because the fluid doesn't have shear resistance, and it can be categorized into the polarization plane. SH, particle motion is horizontal plane, and also the propagate horizontally. So this might be the X, this is the Y, right? And then SB is the particle moves vertically, Z, and propagate in X direction. So then this animation also shows the propagation and the particle motion. So wave propagate to x direction, and particle move up and down in z direction. So this is SV wave. If it moves in y direction, it's gonna be the SH motion. And spherical propagation is a point source in an infinite isotropic continuum. The propagation front is spherical. So you can think of like infinite medium, and inside you have a source of a wave propagation. For example, like dynamite, dynamite buried in soil, deep depth, and it blows and explodes, and it will generate the wave in all directions spherically. So then the Q, the displacement of a particle, can be expressed with this equation. Then plane wave, the difference between the plane wave and a spherical wave, and you have this term 1 over r. That's because of the geometric spreading. So in plane wave, it moves at the same time, like a body wave. But in spherical wave, it's gonna spread spherically with the spherical front, so that the energy dissipates and energy decreases with the propagation. Traveling wave approximates mean propagation direction using the complex number is for the purpose of mathematical convenience. Okay, we'll talk about this later, sooner. The omega t plus minus kappa x. Actually, this is the equation that you end up when you solve the wave equation. And when you solve the wave equation, depending on the frequency you're looking at and the velocity of the media, it gives you a different wave velocity. So for example, the sound wave is it has the like limited frequency range that we can hear, generally 20 Hertz to 20 kilohertz. And if it propagates through the air, the wavelength is 0.0717 meter, so that's about 1.2 centimeter, and 17 meter. But if it propagates in water, because the water velocity is much higher than the a sound wave in air velocity in the air, the wavelength is much longer than the case that the sound wave propagates in the air. Sound wave is still the elastic wave, but that's the when we specifically call the mechanical wave that's in the frequency that we can hear, then it's called the sound wave. And when the elastic wave or the mechanical wave propagates through the Earth's material, then it's called the seismic wave. Okay, so P wave velocity in an infinite continuum, then wave velocity is square root of m over rho, and shear wave velocity is square root of g over rho. So Vp and Vs are not a function of frequency. It means that it's not dispersive media. When it's dispersive media, the wave velocity changes with the frequency. So here we are assuming that it's non-dispersive and elastic isotropic media, so it doesn't have dispersion. Anytime when you have dispersion, it means that dispersion means that any property changes with frequency. and dispersion is also related to the attenuation. So it changes the wave velocity and attenuation characteristic too. So we've seen the propagation velocity. So this Vp and Vs is the propagation velocity. What about the particle velocity? So when there's force, like W is the force, for example, it's an impulse, a step function, and then wave will propagate in the speed of maybe like Vp. If this is laterally confined, right? In this direction is minus infinite plus infinite. Right? But when you think about the particle at B, it can move back and forth during the expansion and dilation by a delta L within the delta T time. So then particle velocity is delta L over delta T. And here delta L is this stress region. If the distress region is L, then L times epsilon. So here the stress region is the it extends to the linearly proportional to the wave velocity. So L over delta T is Vp. Propagation velocity. Then propagation velocity times E epsilon will be the particle velocity. And here the strain can be expressed as Hooke's law, using the Hooke's law, sigma over m, because it's confined condition. It doesn't allow the lateral deformation. So then this will be the particle velocity. So you can see in general, in soil, the constraint modulus is like order of 100 megapascal. And the sigma could be very small. If the sigma is like maybe 1 megapascal or 100 kilopascal, then you can see that the particle velocity is several orders of magnitude less than the propagation velocity. Okay? So that means that here again, if the stress level is high, like this excitation is very high, then particle velocity increases. Then let's talk about the impedance. Impedance is very important. Impedance, there are several impedances in the wave propagation. If it's electromagnetic wave, then you have electromagnetic impedance. And here we are talking about the mechanical wave, so we are talking about mechanical impedance. Impedance is defined as the ratio between the cause and effect. So in the P wave, for the P wave case, Zp is cause over effect, and here the cause will be sigma, which is the stress, and the effects will be particle velocity, right? So then m times epsilon, constraint modulus times the strain that's induced, and the particle velocity is Vp times epsilon. So then here m over Vp, and from the relation the Vp is what? M over rho. So then m is rho times Vp squared. So if you put it in here, plug in, and Vp times rho. So mechanical impedance is velocity times density. And that goes the same for the shear impedance. So shear impedance Zs is Vs times rho. So shear velocity times density. In section 6.5, here we're going to relax the one assumption, which is the infinite space condition. So before we talked about the infinite is like the medium is infinitely large. so that the wave propagates as a body wave, but in many cases there are some boundary conditions. So depending on the boundary condition, for example, an air and media interface, if it's a semi-infinite media, then you get the Rayleigh wave and surface wave between two half spaces, stony wave, Lamb wave in the plate, and lob wave in layers, and rod wave in a cylindrical specimen, and tube wave in the boreholes. So in mechanical engineering or some civil structural engineering, depending on the shape of the beam or structure, you get the different wave mode. Today we'll talk about some representative and most frequently occurred wave mode in particulate media and earth materials. First one is when you have semi-infinite media like air and soil boundary condition. So then within the soil you have P wave and S wave, but at the surface here, at the ground surface, you get the lob wave and the Rayleigh wave. So the body wave propagates within the mass or body, and one of them is P wave, the primary wave, compression wave, dilation wave, longitudinal wave, and the other one is the S wave, secondary wave, shear wave, rotational wave, transverse wave, and distortional wave. When it's surface wave, it propagates along the surface, and it involves the interaction between body wave and the surface. So it generates the lob wave, L wave or lob wave, and Rayleigh wave or the R wave or surface wave. So let's consider a half space where the boundary is assumed to represent the Earth's surface. So then here is the air, and this boundary is stress-free boundary, so you can deform freely without any stress. Two additional surface waves are created due to the presence of the stress-free boundary, which is lob wave or Rayleigh wave. Actually, they are together. Let's look at the surface wave, the Rayleigh wave first. Propagating along a horizontal surface of a semi-infinite medium. So here, when there's force pounding, then surface wave propagates along the surface. Rayleigh wave particle motion is combination of the vertical and horizontal motion. So shear and compressions are combined. Forward up and back and down. So forward up is called the retrograde motion, and back and down, the other one, back and down, forward up. Back and down is prograde. Retrograde is the back and down, and prograde is the forward up. And while the particle motion at the surface is a retrograde elliptic, and it changes into prograde ellipse at depth 0.2 lambda. So at very shallow surface, it's retrograde mode. The particle moves like forward and up, and in deeper depth, then it kind of prograde forward and back, forward and down. So interaction of, I think these two are indicating the retrograde mode together at very shallow surface. Interaction of the P and S, B waves with surface. So you have a compression wave and you have shear wave, but the particle moves vertically in this case. So they are combined in surface in Rayleigh wave mode. Particle motion is combination of the vertical and horizontal. And circle, so you kind of elliptic motion, it shows the elliptic motion. So you can see that it's going up, forward and up, and back and down. So particle moves in circle while the wave propagates in x direction. So when you look at the this animation, it doesn't move, but it kind of moves like this as the wave propagates, like the oceanic wave. Particle motion consists of elliptic motion, generally retrograde elliptical, in the vertical plane and parallel to the direction of the propagation. So here it doesn't show any movement in y direction. So Rayleigh wave involves the movement in x direction and z direction. Velocity of Rayleigh wave r is related to the velocity of the p and s wave. So here the Rayleigh wave is correlated to shear wave velocity and the p wave velocity. So you can see the VR, the Rayleigh wave, is function of Poisson's ratio and the shear wave. VR is the Rayleigh wave velocity is non-dispersive in homogeneous elastic half space, and it measures dispersion reflects on near surface conditions such as changes in elastic properties with depth or the presence of anomalies. So we use this assumption to get the shear velocity profile from SASW. The other type of surface wave is lobe wave. This is the first kind of surface wave and named after A.E.H. Loeb, British mathematician, and fastest surface wave, and it moves ground from side to side. The other one is Rayleigh wave. It's much larger than the energy is much larger than the other waves. So most of the shaking felt from earthquake is due to the Rayleigh wave. And if you see the animation, this one moves, the particle moves in this direction, horizontal direction. So particle motion consists of alternating transverse motion. Particle motion is horizontal and perpendicular to the direction of propagation. To aid in seeing that the particle motion is purely horizontal, focus on the y-axis as the wave propagates through it. Amplitude decreases with depth, and material returns to its original shape after a wave passes. So at the surface, you have the largest amplitude, and as you go deeper, the amplitude decreases. So when we compare the P, S, and the Rayleigh wave and Loeb wave, I kind of summarize this here. And in velocity-wise, P wave is the fastest, and shear wave, and then surface wave. Actually, the shear wave and the surface wave, they are quite similar. The magnitudes are, and magnitude, P wave and the shear wave and the surface wave. Surface wave is the greatest and it has the greatest energy, and then shear wave and the P wave is the least. So this kind of shows the characteristic very clearly. And when you pound with a hammer a disc on the ground surface, it generates the P wave compression and S wave and Rayleigh wave, right? And percent of the total energy, when you look at 67% is the Rayleigh wave, and 26% is shear wave, and only 7% is the compression wave. And that's because of the geometric attenuation via subthreading, and material attenuation is big. And you can derive the Rayleigh wave attenuates proportional to the 1 over square root of r. So because it propagates along the surface, not going into the body, wave attenuation, energy dissipation is slower than the shear wave or the compression wave. Compressional wave, it can propagate spherically, right, in 3D, but Rayleigh wave, it propagates like a disc type of spreading in 2D. So that's why the wave attenuation is slower than the body waves. And the other one is a rod wave, long structure cylindrical specimen is torsional wave. If it's torsional, then it's the same with the shear wave. Velocity of the torsional wave is the same with the body S waves. And if it's longitudinal wave, then because it causes the lateral deformation, longitudinal wave is correlated to the E, the Young's modulus, that occurs the lateral deformation. And if the wave length is much smaller than the radius of the specimen, then it will correlate to the P wave. So here, if you have a specimen like this, and this is the R, if the wavelength is very small, then it won't cause the lateral deformation. But if the wavelength is very large, like this, then it will cause some deformation, lateral deformation. So it causes the Poisson effect. So then, in this case, excitation will cause the longitudinal wave velocity. In this case, the propagation velocity will be close to the P wave velocity. So depending on the lateral straining, the boundary condition can be neglected if the wavelength is very small. If wavelength is very large, then you cannot neglect the boundary condition. We're gonna talk about this in detail in the class. And also the flexural wave is like this. And when you hit it in this way, then it moves this and going back and forth, and while flexural wave propagates. And this is correlated to the longitudinal wave or the rod wave with the wavelength. And now we're gonna relax the homogeneity. So we'll talk about the effect of discontinuity, the reflection and transmission. We'll see some movie in the class, or you can Google the wave propagation at the boundary. Then it will show the effect of boundary condition, whether it's fixed or free end. So this is the case. If wave comes here and there's some discontinuity and the material changes, and here's the mechanical impedance is E1, which is rho 1 times V1, and this is the mechanical impedance Z2, this is the medium 2, and rho 2 times V2. So then, depending on if Z1 is larger than Z2 or the other way, propagation is different, and reflection, transmission and reflection behaviors are different. So reflection coefficient can be defined in terms of the particle displacement, R displacement, as a function of Z1 and Z2, or stress. And transmission coefficient T also can be defined with the impedance Z1 and Z2, depending on in terms of displacement and in terms of stress. So example is if it's free end, so here Z1 is larger than Z2, very much larger than, then R1, the R displacement will be 1, which is larger than 0, and R stress will be -1. In this case, because of this, Z2 is 0. And if it's free end, let me show you some result. this is the free boundary, and if wave comes like this, and it just bounces back as positive polarity again. But in terms of stress, if there's a positive stress coming in, and when it meets the free boundary, then it flips, it goes to negative polarity, or the negative stress. And if it's fixed end, then now Z1 is smaller than Z2, then R displacement will be less than 0 or close to -1, and it could be positive. R stress will be positive or close to 1. So then it's gonna be the other way. Yeah? So here, if the displacement, positive polarity in terms of displacement is coming in, then it flips back to negative. And if the stress, positive stress is coming in, then it will keep its polarity as positive. So this is the same with like reflection and transmission. When you shout in mountain, it just bounce back. But sometimes the polarity becomes changed. We'll see more figures and animations in the lecture. If there's more than 2 materials, then there are 2 layers, the boundary interface like this, then the transmission coefficient or reflection coefficient becomes much complex. The transmission coefficient is complex in a 3-layer medium to capture the phase shift or time delay as the wave travels through the middle layer. So now you have complex number I. What about when you have oblique incidence? So before it was the incident is just orthogonal to the interface. But now incident angle is not 90 degrees, so it's oblique incidence. And the particle motion can be converted in different ways. So SH wave, if it's coming in, then you get the SH. And when you have a SV wave, then it will move like this. Then you get the P wave. It will move like this. Then you have a P wave and the SV wave together. So shear wave that's polarized vertically, if it propagates and it meets the when it propagates downward and it meets the interface, it can generate the P and SV wave together. What about the P wave? If the P wave incident obliquely, then it can generate the SV and the P wave at the same time. So, and this is called the mode conversion. And these are all, it can be all solved based on the Snell's law. And the Snell's law, I think we've learned it, if you refresh your memory, from the elementary physics in your freshman year. Compression mode, when it angle is just right, then they just go through the boundary, not transmitting or not reflecting. And this critical incident angle IC is defined as sine, the arc sine of VP over VP, VP soil or VP rock. So this is the soil and this is the rock. Angle of reflection and refraction, that's depending on the velocity, right? So here, using the Snell's law, depending on the velocity of the medium, the V1 and V2, then this angle reflection is defined. And there are tables in textbook. It shows the and derive the amplitude of resultant wave when you have oblique incidence. So in the homework, we're gonna plot this one for several cases. This is the end of lecture 2. Thank you.